What's good? What's good? What's good? Still on chapter 3 today. I think we're on this question. No, we aren't. Uh, Hold on. Show that if Dn is bro, this is just more math. Hmm. So I guess what we basically saying is Okay, what if we take the contrapositive? So ADN then bro, this is Okay, since we say that a function dn is OFN if it for some constant c bigger than or equal to bigger than 0 and an integer constant n not bigger than or equal to 1 such that f of n smaller than c of gn for we can let g of n equal adn since a is the case ca tn will always be bigger than dn. So this still satisfies the definition of big O. And since ADN is yo, this might be the most chopped answer in history. I'm gonna ask ChatGPT what it thinks. Is my answer correct? Oh, man, yeah. All right, I pretty much, pretty much did the same thing. Just, bro, it took us 15 minutes to do one problem. Why do I have to prove this stuff? Alright, I'm gonna Wikipedia this shit. Like I'm not gonna come up with the proof of this on the spot. Nah.
Six nights with the family, 4 nights for work. Adds up. Hello, everybody. I hope everyone's having a wonderful day. So today we're going to be proving another property of big O. It's called the product rule of big O. So the statement of this is going to look a little complicated at first, but I assure you it's actually quite simple. And at first it will also look like something a little bit strange, or you might ask, Dan, what does this have to do with me analyzing algorithms? And I'll explain in a moment. So the statement of the theorem is if F1 is big O of G1 and F2 is big O of G2, then it must be that the product of F1 and F2 is big O of the product of G1 and G2. So just to motivate why exactly you might be interested in this property, it is very much the case when we have an algorithm that has a so-called nested loop. So for example, you might have a for loop embedded with another for loop. You may count the number of times an inner loop iterates, or the amount of work that occurs or number of operations that happen within that loop. This may be, for example, F2, and F1 may, for example, be the amount of operations that occur on the outermost loop. So this would be, say, the number of iterations of the outermost loop. That would be most likely what F1 would be. So what this statement is that if you know that F1 is big O of G1, and you know F2 is big O of G2, then the result will actually be the product of those two resulting functions. Seems pretty straightforward, right? So this, you can encounter this and use this when it comes to nested loops. Just be very careful when you're counting. Sometimes you don't necessarily need this property at your disposal. It's just something nice to know. So anyways, let's prove this statement. So what do we usually do when we prove statements like this? I give you a game plan. So some rules that I'm going to follow. So that way I communicate clearly to the reader what exactly I'm trying to do. So I'm going to say in order to prove the claim, we find constants c, which is a positive real number, and n0, which is in fact what? It's a positive integer, right? A positive integer. Such that for all n greater or equal to n0, for all n greater or equal to n0, it must be that f1 of n times f2 of n is less than or equal to c times g1 of n times g2 of n, right? So now this is where it times g2 of n, right? So now this is where in our proof we would like to use things we know in advance based on the conditional. So we know if we want to show, given these two facts, this follows. So we're going to use these two facts that I have right here. And what are those facts? What are those two facts? They are, in fact, that we have two big O statements. I'm going to use them in the definition. I'm going to invoke both in the same sentence. So just read what I would write down here very carefully. So what am I going to do? If F1 is big O of G1 and F2 is big O of G2, then by the definition, definition of big O, what can we say from the definition of big O? That there are exists constants for each one of these two statements. These two I've just stated right here. There's constants that exist. So I'm going to list those out such that certain inequalities hold, right? By the definition of big O, there exists C1 and C2. I'm just giving them names. These are positive real constants, right? One for each invocation of the definition of big O. And N1 and 2, which are going to be positive integers, such that both the following things are true for such a statement.